what else do we need to know about that whole thing? Okay. So this is, we talked about two ways to say how electrons are configured, and I'm not going to go back over the other way, but the other way is box and arrow notation. So I'm anxious to kind of look at your homework and make sure we're on the same page with regard to box and arrow notation, because that'll be on the test too. So we talked about names for different groups, and that group 8A actually has 3 names. One of them is rare gases, inert gases, and noble gases. That's 8A. And we said that as we were hopping along, loading electrons, saying how they're configured around the nucleus of an atom, if you bump up against something that is something P6, right at that point, you have basically loaded electrons, finished topping them off into something that's a rare gas. We're going to talk about compounds, whether we started on Wednesday, most likely. But when we talk about compounds in Unit 3, we're going to see that atoms like to connect together to make a repeating unit because they want to get 8 electrons. And do you guys see where if you take 2 plus 6, you get 8 electrons? Okay? That actually is something we're going to call a complete octet later on. Okay? Oh, there it goes. There's my whole in italics, exactly what I said. That's so exciting about, for instance, just a cute little water molecule. I think atoms are overlooked. I think molecules are overlooked. You know, it's only to me, and I know I'm biased, but it's only to me until you understand the very small things can the larger things make sense. Okay. So not all electrons are created equal. The electrons that are actually going to be involved in making chemical compounds, electrons are going to be involved in chemical reactions, are the valence electrons of an atom. Valence electrons are not the last added. Valence electrons are the highest N of the subshell they're hanging out at. So if we go over here to tin, okay, what's the highest N in all this blah, blah, blah? What's the highest N of a subshell?
5.
I got 5. Yep. Yep, exactly. It's tempting to say the 4D10, but the D type is the highest type of subshell, orbital type. But the highest N is 5. N is equal to 5. So all this is saying is if I want to find the valence electrons around a tin atom, I have to find all of my 5s. That's it. So how many valence electrons does tin have? It has 4. All right. What group number is tin in? Remember, group numbers at the top. Those are kind of important. It's Roman numerals IV, which stands for 4. So bada boom, for the A elements, we talked about how the periodic table is chunked up. We have 2 columns of A here, then we have kind of the B's, then we have 6 columns of A's over there. The number of the group for the A's are the number of valence electrons. Is that not fun or what? I think so. So I have a couple figures to kind of emphasize valence electrons. This is silicon, not silicon, silicon. Yep, I know. It's not really funny, but it was kind of. So 14 electrons around a silicon atom, okay? Notice that silicon is in period 3. Period 2 noble gas is period 2 noble gas is neon. Exactly. Period 2 noble gas is neon. How many electrons around a neon atom? 10. Okay, my only point is how many electrons are here? 10, right. Okay, so this figure is kind of emphasizing that. So beyond the 10 to get to silicon, we need 4 more. And using the arrow diagram, here's where we place the other 4. We would put 2 in the 3s and 2 in the 3p. So silicon is actually in the same group as tin, 4 valence electrons. There you go. So let's go up a little bit higher. Selenium. Selenium is in the same group as oxygen, sulfur, selenium, tellurium, polarium? Okay. So how many valence electrons should selenium have? 6. It should have 6. Yep. So let's look for them. This, by the way, is the abbreviated rare gas notation you might use for what? Argon. Okay, so this is in the period before selenium. So argon is 18 electrons, and the electrons beyond argon would look like this if you were using the arrow diagram. 4s2, 3d10, 4p4. Now I said you identify valence electrons by the highest n. So can you see where, I don't know if you colorblind people in here, it happens, but the yellow marks the valence electrons, and n is equal to 4. So we have 6 valence electrons. Selenium is a group 6A. That's perfect. Okay? So here's now where I get to tell you something kind of an aside for this course anyway. Well, I don't know, could I include on a test? I guess I could include on the test. This actually, our arrow diagram follows the lowest n plus L rule. Okay? And it works usually. The exceptions occur, when the exceptions occur, actually, they make sense too. So this is an application of n plus L rule. Okay? And the first exception starts at chromium, which actually has 24 protons, so the 24 electrons around a chromium atom don't follow the n plus L rule. Will I pull that out on a test? No. Do you kind of have to have a reason, know why they don't behave like we think they should? Yes. Okay. So here's chromium. Here's the 24 electrons around a chromium atom. Okay, this is in what we say the order of filling. Okay, this is using the arrow diagram. If we were to unscramble it, kind of like we did on Friday, we'd take that 4s2 and we'd move it this way. Okay, so this is actually in the order of increasing n. The only reason you'd want to unscramble this, so this is the same configuration, but moving the 4s2 out. Okay, this way of rewriting it in order of increasing n emphasizes the valence electrons. Then you don't have to search so much for them. Okay. So this is, if I asked you on a test, this is what you would say. I'll tell you though, this is actually what chromium does. Okay, if we kind of compare the last one with this one, okay, you're like, all right, so what must have happened? Well, it's kind of a switcheroo right here. Right in the last 2 subshells. Okay, so in other words, basically this one electron that we think should have completely filled the 4s subshell before going on to the 3d subshell jumps ship. So D-type, you guys told me a D-type subshell can accommodate 10 electrons. What is 5 relative to 10? Half. That's exactly it. And what's 1 relative to 2? Half. So that's an example of basically it's a more stable electron configuration for chromium to take one of its electrons and to go ahead and jump ship up into the higher energy. So it does. So when do they occur? They occur like we just saw with chromium, to half fill a D-type, to completely fill a D-type, to half fill an F-type, which would be F7, or to completely fill an F-type, which is F14. Now, you definitely don't need to memorize these or even chase them down, I don't think. Earlier, when we were talking about the periodic table, since we're focusing on elements for Unit 2, you do need to know the names and the symbols for some elements, and you do need to focus on that. I gave that by atomic number. These actually are where the exceptions for the lowest n plus L rule occur, starting with atomic number 24, chromium. So on a test, I'm not going to ask you these. Or if I do, just use your error diagram and be oblivious to the whole thing. Okay. So now I'm getting ready to show you one more way of coming up with how electrons are configured around an atom. I hesitate to show you this because it can get a little bit confusing. If you need to come up with electron configuration, the arrow diagram will always work for you. In fact, sometimes even with the shortcut I'm going to show you, I refer back to my arrow diagram to make sure I have it right. But there's this cool way of, and you'll want to know this anyway, of chunking up the periodic table. So we chunked up the periodic table before, and we're going to chunk it up again. So the, alkali metals and alkaline earth metals, 1A and 2A, those guys, okay, we actually, as we're adding electrons, the last electrons to be added are S-type electrons. So we collectively call those two groups the S-block elements, okay? These, I'm going to skip over here to the other group A elements. We'll come back to the B here in a minute. But if we go, remember A, we have 1A, 2A, and then we skip over here, 3A, 4A, 5A, 6A, 7A, and 8A. 3A through 8A, those 6, this is kind of cool. So you guys told me 6 electrons in a p-type, right? How many rows are there? There's 6. 6, I meant to say columns. There's 6 columns. That is so fun. Okay, it makes sense. Okay. All right, so S block, P block. Now, D block is these guys right here. So as we are jumping and skipping along, like for instance, we did one, let's see, I can't remember what we did. Did we do iron maybe? I can't remember what examples we've done. But for instance, if you take iron, Fe, my goodness, iron is smack dab in the D block elements. Okay, so when you start to kind of peter out electrons, the last to be added are going to be in the D type. Here's the catch. The last to be added are going to be in the N-1, where N is the period. So I can tell you right away, let's pick on iron, okay? I would, using this method, here's how we go. Iron, what's the rare gas I can base it on? So it's in the period before iron. Argon, exactly. So if I were going to say, how are the 26 electrons around an iron atom arranged? I would do this. Argon. Then after argon, it's kind of jumping and skipping. So I come to potassium and calcium. Those are S block, right? And they are in period 4. So I would put 4s2. 2 electrons, kind of jump along. And then I bump up against scandium, titanium, vanadium, chromium, manganese, and then iron. Okay, I'm entering D block, but it's N-1. So here's what I mean to say. Instead of being 4D, it's 3D. That's the N-1. And how many did I jump over? 1, 2, 3, 4, 5, 6. That's it. Okay? Again, I hesitate to show you this because there's a chance it can get balled up. But it's kind of nice. You can kind of quickly knock out, especially based on rare gas, abbreviated rare gas notation, how the electrons are configured. Any questions about this?
So for the rare gas, you put the rare gas in brackets, and that's where you start with your electrons, and then from there you do like 4s2, 5.
Right.
So
Yep.
within that whole block, it's going to be N-1. So you're going to go back from
Right. Whatever the period is, it's D, but it's
-1.
right.
Okay,
Yeah.
So
So
if we start in period 5, it'll automatically.
like
be-
molybdenum, you know what I mean. Molybdenum
Yeah.
would be what? 4D. Yep.
Okay.
Okay. I have one more thing. Now, the group we didn't talk about are the green guys down there. Okay. They are. Yep. This is so cool. If you count the columns, I know I'm a geek, but there are 14. There are 14 columns. Okay. So actually, as we skip along the actinides and lanthanides, we are adding F electrons. They are the F block. They are the F block. Okay, but there's a catch to them too. They are N-2. Like, oh my gosh, are you serious? Okay, so the lanthanide series inserts there at, looks like what, period 6? So N-2 means, for instance, if we pick on uranium, well, uranium is actually inserted in period 7. Are we all good with that? Now uranium, I'm just telling you up front that I would use the arrow diagram or a combination of the arrow diagram for uranium. But I just want to emphasize, if we were seeing how the electrons kind of peter out there, we're talking, what, 7 minus 2, so that's 5F. Okay? And this is where I get kind of confused. To me, it looks like 5F3. But I would use the arrow diagram. Are there any questions about that? Okay. Because I get confused where the D's or what, I don't know. Okay, I don't like to think that hard. Okay, very good. So these will be due on, just give you a little more exercise. These will be due on Wednesday. Remember, did I last time, when we got to near the end of a unit, it seems like I took my homework answer keys in doc sharing and I just put them all out there. I think I'm going to do that again. I'm just going to go ahead and, so if you look at doc sharing for the answer keys for homework, I'm just going to make them all available. So these will be due on Wednesday. We'll take a quick look. And then we're going to talk about atomic size here. Yay. Okay. So these aren't too bad. These will be kind of similar to what you did. Write orbital diagrams. Now, orbital diagrams are box and arrow notation. So for the first one, box and arrow notation. Box and arrow. They shouldn't be too bad. The problem is, like, if you have to do a box and arrow notation of something like, you know, something big, like 10, 50 electrons, okay? It can be done, but. The next one is write electron configuration. Electron configuration is spectroscopic notation. So that's the non-cramped.
So that's the one with the noble gas where you put it in.
Nope, it could be. But spectroscopic notation is just that 1s2, 2s2, 2p6,
Oh, okay, so that
3s2. Yeah, that's spectroscopic notation. Let's see.
It does say to use.
Yeah, this does say, yeah, that's spectroscopic notation. This one does say go ahead and use the rare gas notation. So you're right, JC. For this one, they want you to go ahead and, you can write both out if you want. If you're like, I'm not sure about that rare gas, well then write them both out. Okay. On my test, I'm going to make the abbreviated rare gas notation optional.
Okay.
So you're right, very good. And then 56 is, again, spectroscopic notation, transition elements. 58 is electron configuration and indicate the valence electrons and the core electrons. Okay? That's not too bad. And then the next one looks like this. This is kind of fun. It's kind of like scavenger hunt, right? So sometimes my tests have kind of taken on this sort of approach. Given the periodic table, find the element in the fourth period with 5 valence electrons. So what group are you going to look in for 5 valence electrons? 5A, yeah. So a total of 3 d electrons, a total of 3 d electrons. Oh, that's a good one. Remember, d is n minus 1, so what period you're going to look in? The other way. So not 2, but 4, yep. If you look in, and you look in n is equal to 4, yep. Period 4, yeah. And then 76 is kind of fun. It gives you, using abbreviated rare gas notation, how electrons are configured, and you have to say what element that is. I'm like, you just have to count superscripts, like, because that's electrons, right? Beyond the rare gas.
So the first one would be neon plus 1.
Right. It'd be neon is 10, yeah, plus 1.
Sodium.
Sodium, yep. So that one's kind of, again, a little scavenger hunt. Okay. Well, I want to at least begin the next part. If technology will cooperate. A little sketchy. But my recording didn't work very good Friday, but I think it was because it just had too much stuff in it. I was not happy about how big is that atom? So So we talked about subatomic particles. Which subatomic particle is on the outside? Valence electrons, but just electrons in general. We're switching gears. We're not saying how they're configured, but electrons are the outermost particle, exactly. And we actually did do a, we actually did do kind of a thought exercise of, is there a lot of space between the nucleus and the electrons? Yeah, it's just, and I heard recently that if you take a blueberry, and that's the nucleus, then you put it in the middle of a stadium, and then that's kind of drawn to scale what the nucleus is and where the electrons are. So I think that's kind of cool. It's still kind of okay. Well, it's all about the electrons for giving an atom a certain volume. Well, on your next slide, do you have the, speaking of volumes, so I'm just kind of, I looked at it recently, so we are in part 6. Yes, it looks like this. Okay. So how big are atoms? And I'm not going to have you guys do this sort of thing, but we could come up with kind of how big of an atom is dictated by where the electrons stop. Okay. As I was getting ready for this, I thought, now we just recently talked about different electron orbital shapes. Like they're not all spherical, they're not S. We have a dumbbell, but just for now, kind of think of them as all kind of working together to make a sphere again. Okay. Let's see. So you're not going to have to do that calculation. But I guess if I was going to go back to that equation, volume is related to radius, okay? And so actually here in a minute when we talk about how big an atom is, we're going to actually be talking about the radiuses from the nucleus out to the edge in general of the electron cloud. Whether that's an electron cloud, is an S-type, P-type, D-type, or F-type. We're just going to kind of go ahead and say spherical. So here we go. This is one of the things you're going to want to know. How, if you look at a periodic table, how does the size work with regard to the atoms? And you might say, well, you know how it works because it's increasing, 1 through 10, then we go 11 through 18, It just does that, right? No. Sorry, I wish it did, okay? But actually, as you're in the same group going down, okay, it does get bigger. The atoms do get bigger. Unfortunately, and we're just going to focus on the A group elements, don't blame me, and I'll try to tell you why this is. If you are jumping from left to right across the same period, they get bigger. Or, excuse me, they get smaller. They get smaller. Isn't that just so frustrating? So they get bigger actually going from right back to left again. So one of the things that you're going to be tasked with, for instance, on your test is, which is bigger, fluorine or lithium? And you're like, well, fluorine's got to be bigger because it's got 9 protons and 9 electrons. But as it turns out, since they are in the same period, lithium is bigger than fluorine. So that's the only weird thing that I got to tell you.
But if they weren't in the same period, like if you were to do like potassium and phosphorus or something, they would be
right.
phosphorus would be bigger.
Let's see, you said potassium and phosphorus. Yeah. In that case, well, then we still have the same sort of trend going. Kind of for a different reason, potassium is going to be bigger. But I think what you maybe meant to say, if I go lithium and phosphorus,
Yeah.
okay, lithium and phosphorus are in 2 different periods. Phosphorus would be bigger. But sodium and phosphorus, sodium's bigger. You see how that is?
Mm-hmm.
Yeah. Okay, so that's kind of, this slide right here, if you want to put a star next to it, part 6, this is the crux of part 6. This is totally the crux of part 6. They get bigger as they go down, and they get bigger if they're in the same period, going from right back to left. Okay, but I'm going to kind of talk about why that is. That's it. Oh, see. Also, though, notice that I am kind of qualifying this statement by saying the main group elements. What are the main group elements? Remember?
A group A.
They are group A. Main group elements, group A are the same thing. And I'm going to show you a slide to how the trend is with the other elements. So these are just the main group elements. This is basically taking those nasty transition metals and taking them out. So we squished 1A and 2A. We picked up the 3A through 8A and squished them together. So that's kind of nice. All those cute little balls. Now again, here we're talking about the overall size of the atom. Those aren't nuclei, those are sizes of the atoms. This is just looking at a different way, some different colors showing the different types of elements. Okay, of course we have metals. The green would be what, metalloids, and the yellow would be nonmetals, what we talked about. And here we actually have some quantitative data. In terms of one of the prefixes I didn't have you memorize is pico. The prefix pico means 1 times 10 to the negative 12th, or 1, is that 1 billionth? Yeah, 1 billionth of. So how the radius of an atom from the nucleus out to the edge of the electron cloud actually is a player when that atom goes to connect with another atom. So here we have a couple of situations. We have 2 carbon atoms connected together. If you look back at the radius of a carbon atom in picometers, it's about 77. So if you take 77 times 2, you get what, 154? Yeah. See how that works? Thank you. The chlorine radius for a chlorine atom in picometers is 100. So, or maybe it was 99. Okay. So actually, as they join together, we can get a sense for what the bond length is going to be for these types of compounds anyway. Okay, so the the trend, if you go down a period, makes a lot of sense, I think, because you got a whole bucket load of electrons on, extra electrons. So for instance, if you compare lithium to sodium, sodium's bigger. Sodium to potassium, potassium's bigger. Potassium to rubidium, rubidium's bigger, okay? And we just got a whole bunch more electrons there, okay? The trend of size getting smaller as you go from left to right in the same period is not as easy to explain, but it can be explained if we talk about attractive and repulsive forces. So I think that's a good place to start because we'll get a running started on Wednesday. So we'll finish up this thought on Wednesday, and I'll go ahead and assign that assignment slide on Wednesday, which you should be able to do right now, because that assignment slide just has the arrows of, you know what I mean, are they getting larger as you go down and larger as you're going from right back to left again. Okay, so we'll see you on Wednesday.